The trickiest part about today's lab is to turn this, the polypeptide in extended conformation, into this, which is an alpha helix. The easiest way to do this is not by trying to assemble the polypeptide and make it look like the picture, but rather to take the polypeptide that you've made in extended conformation and to rotate the bonds on it until it is in the shape that you see right here. So the first thing that you have to figure out is which way is up and which way is down. Is it this way or is it this way? Well, obviously in real life atoms don't have any up or down, but in terms of up and down relative to this diagram, we're going to call the N-terminus down and the C-terminus up. So one of the things that you have to keep in mind that's important is that anytime you make a model with the pushfit, you're always going to have part of an incomplete amino acid. Remember we talked about this rigid polypeptide bond that won't rotate? So basically this polypeptide bond is the end of a complete amino acid. So this little carboxyl carbon that's sticking out beyond that is an incomplete part of some other amino acid. So this nitrogen here is the actual end of the polypeptide chain, and we're going to pretend that this part doesn't exist here. So that's the N-terminus, and that's what we want to have at the bottom. On the other end, this is rotatable. Here is the non-rotatable polypeptide bond, so I'm just going to mark that here. That's the end of the amino acid at the other end of the polypeptide chain. This is the carboxyl carbon, so this is the C-terminus. So that's how I know that this is oriented correctly and that it should not be like that. So let's start down at the bottom where the N-terminus is. And notice that according to this diagram, the N-terminus, the hydrogen atom, is pointing down. So the trick that we're going to do to turn this thing into an alpha helix is simply make sure that all of the oxygen atoms are pointing up and all of the hydrogen atoms are pointing down, and at the same time all of these gray R groups are pointing sort of outwards and downwards. So here's how I'm going to do it. Turn this around, make the oxygen point up, hydrogen points down, our group is pointing down and out. Take this oxygen, make it point up, make this hydrogen point down, our group points down and out. Oxygen up, hydrogen down, our group pointing down and out. Oxygen up, hydrogen down, our group pointing down and out. Now you'll notice that when I do this, it's already starting to form itself into a helical shape. So I'm just going to continue doing this for the rest of the amino acid residues. And back around to my last oxygen, and voila, I have made a helix. Now, it is possible to make this thing rotate in the wrong direction. The direction that the helix is going now is what we call a right-handed screw. If you move your fingers if you move your hand in the direction that your fingers point on your right hand, your thumb shows the direction that you're moving, which is up, and that's the kind of screw that we have here. If we don't swing the R groups down and out, if we make them go up relative to the orientation we have here, then it helicizes in the wrong direction. So watch what happens. If I swing this R group up instead of down, now the helix is going around like a left-handed screw instead of a right-handed screw, and this is a common mistake. So I'm going to go ahead and swing these around again and make them point down, and now I have my beautiful alpha helix. Now the one thing that's still left here is how tight should the helix be? If I twist it like this and make it tighter, then it's thinner and longer, whereas if I twist it like this, then it's looser. So how do I know how much to twist the helix in order to get the right amount of turns in it? Well, the answer is that from X-ray crystallography, we know that there's about 3.6 residues per turn. So I'm going to pick a particular starting point, like this oxygen atom here, and I'll count from it 1, 2, 3. So there's 3, and then here's 3.5. So this hydrogen atom here is the one that I want to line up with the oxygen atom that I started with. So this is going to be a hydrogen bond between those two atoms. And in fact, that's why the trick works of pointing oxygens up and hydrogens down, because that's the direction they have to be oriented in order to get the series of repeated hydrogen bonds that holds the helix together. So now I just take the next hydrogen and the next oxygen and make them line up, the next hydrogen and the next oxygens and make them line up. And now I have done it. I have created an alpha helix that looks just like the picture in the book.